Chapter 9, Chemical Equation Calculations. We've done chemical equations, and now we're going to look at them in terms of applying them to more practical things. If we look at this chemical equation, this is describing how nitrogen monoxide from exhaust reacts with oxygen and forms nitrogen dioxide gas, which has got kind of a brownish color, and that's what makes smog brown. So 2NO gas plus O2 gas. This is catalyzed by ultraviolet light. Gives us 2NO2 in the gas form. And so we have learned what these equations are. We've learned how to write them, how to classify them, how to balance them. Now we're going to talk a little more about what they mean. So this, of course, can mean that we have two molecules of NO, and here those are drawn out. There's pictures of two molecules of NO and one molecule of oxygen, and those combine to form two molecules of NO2. So that's the molecule interpretation of this chemical equation. But could we also say that 24 of these react with 12 of those and form 24 of these? Could we just multiply everything by 12? Would that still be? Yeah, sure, that would be fine. So we could say we've got 24 plus 12, and that gives us 24 of that one. Well, the dozen is a counting number. Chemists use a different counting number, counting unit, the mole. So we can also say that we have if we have 2 moles of NO plus 1 mole of O2, we're going to get 2 moles of NO2. So any balanced chemical equation we can interpret in terms of molecules, but also in terms of moles of molecules. And so that's what we generally do. We just sort of mentally insert the unit mole. Mole, mole. There's not a 1 written there, but we understand that that's 1 mole. Any questions? You okay with that? We can also have a volume interpretation of equation coefficients, and this applies to gases only. Avogadro's theory was that there are equal numbers of molecules in equal volumes of gases, provided that the temperature and the pressure are the same. So if we look at our mole interpretation of that previous equation, 2 moles of this react with 1 mole of oxygen and form 2 moles of NO2. Each mole is going to have a particular number of molecules in it. And for gases, if the number of molecules is the same, then the volume is the same. So remember that 22.4 liters per mole at STP. So we could go through here and calculate the volume in liters at STP. This would be 2 times 22.4, be 44.8 liters of NO plus 22.4 liters of oxygen would give us 44.8 liters of NO2 at STP. Because 2 moles of NO2 occupies 44.8 liters. This is the molar volume of any gas, right? Any questions? So we could use this to convert But the cool thing about gases is, even at other temperatures and pressures, as long as you're not changing the temperature and pressure, if you have equal numbers of particles, you have equal volumes. And so instead of mole in this equation, we can put any convenient volume unit for gases. So we could also write this as 2 liters of NO plus 1 liter of oxygen would result in 2 liters of NO2. You could use gallons, you could use cubic meters, you could use any unit that you want as long as the unit is the same for each of them. So we could say 2 milliliters of NO will react with 1 milliliter of O2 to form 2 milliliters of NO2. Only for gases. It's tempting to use it for other things, but you can't. The only reason we can do this is because of Avogadro's theory, which has been tested and is correct. That equal volumes contain equal numbers of molecules. And the chemical equation has to do with numbers of particles interacting with each other. Any questions? So this is an example. Here's a generic equation. 2A plus 3B forms C plus 2D. So we can interpret this in terms of molecules. 2 molecules to 3 molecules to 1 molecule to 2 molecules. We can interpret it in terms of moles. 2 moles to 3 moles to 1 moles to 2 moles. Or ratio of volumes of gas. 2 to 3 to 1 to 2. So the chemical equation is a really, really useful thing, and it can be sort of tailored to whatever situation we're dealing with. But it is important to understand that for the gases, they have to be at the same temperature and pressure. And in this course, that's all we're going to run into. When you take 1A, they'll step it up on you. But for this class, they're always going to be the same. So those coefficients give us a mole ratio of reactants and products. And the mole ratio can be used as a unit factor to convert from one substance to another. Given the chemical equation for the combustion of propane, balance the equation and interpret the coefficients in terms of moles and of milliliters. First thing we have to do is balance it. Here we've got 3 carbons, and we only have 1 over there. So let's start out by putting a 3 here. This is a review of equation balancing. And next we should look at the hydrogens. There's 8 here, and there's 2 there. If we multiply that by 4, we'll get 8. Now we have a total of 4 oxygens here, and 3 times 2, 6. 4 and 6 is 10. And so I need a 5 here. And now I have a balanced chemical equation. Just remind you that the final exam is cumulative, and the way to retain the information that you've learned is to keep using it and keep practicing it. So in terms of moles, how many moles of C3H8? 1. 1 mole C3H8 plus how many moles of O2? 5. All we're doing is inserting the unit mole between the coefficient and the formula. So then that becomes 3 moles of CO2 plus 4 moles of H2O. These are all gases, and so we can also interpret them in terms of volumes. It doesn't have to be liters. Milliliters is fine. So this could be 1 milliliter C3H8 plus 5 milliliters of O2 to 3 milliliters of CO2 plus 4 milliliters of H2O. Any questions? Remember the law of conservation of mass? Mass is neither created nor destroyed during a chemical reaction. And we can confirm this or verify this looking at these equations. The combined masses of the reactants must equal the combined masses of the products then, right? If we can't create or destroy mass, then all of the mass that we start with must show up as mass of the product. And honestly, I can't remember exactly what I was planning to do with this slide, but I'll make something up. So we can interpret this as 2 moles of this reacting with 1 mole of that. Well, what's the mass of 2 moles of NO? Well, nitrogen is 14.01 and oxygen is 16. So 1 mole is 30 grams, and I'll multiply by 2. So that would be 60.02 grams of NO. And this is 1 mole, going to react with 1 mole of oxygen, which would be 32 grams. And let's see if that equals the mass of 2 moles of NO2. That would be 2 times 16 plus 14.01. Each of these, bless you, weighs 46 times 2, 92.02 grams of that. That was kind of high. Well, 60.02 plus 32 equals 92.02? It does. So that obviously is not proof of the law of conservation of mass, but I think it's helpful to look at.